Welcome to definite integrals and u-substitution. So recall the fundamental theorem of calculus. Says if lowercase f is continuous on the closed interval AB, and if capital F is an antiderivative of lowercase f, then the definite integral from a to b of lowercase f of x dx is equal to capital F of b minus capital F of a. And again, remember that way I wrote this with the notation capital F of x, then a vertical line with a subscript of a and superscript of b. So once we involve u-substitution, there are essentially two ways we can evaluate our definite integral. So method one is if the integral involves u-substitution, we can find the antiderivative in terms of x, or find an antiderivative in terms of x. And then apply the fundamental theorem of calculus in x. So for example, if we wish to evaluate the definite integral from 2 to 4 of x times cosine of 3x squared plus 5 dx, we could first find the indefinite integral of x cosine of 3x squared plus 5 dx, trying to find an antiderivative. For this particular problem, our inside function is 3x squared plus 5. So we'll go ahead and set u equal to 3x squared plus 5. That means that du is 6x dx, or x dx is 1/6 du. So we are looking at the integral of cosine of u, and then that x dx becomes 1/6 du. This integral is 1/6 sine of u plus c. If we go ahead and plug back in, u equals 3x squared plus 5. We have 1/6 sine of 3x squared plus 5 plus c. Our next step from here is to then apply the fundamental theorem of calculus. So at this point, we have found an antiderivative. It's relatively quick to finish from here. We have that our definite integral from 2 to 4 of x cosine of 3x squared plus 5 dx. And that was our original definite integral. This should be equal to our antiderivative, 1/6 sine of 3x squared plus 5. And then that vertical line evaluated at 2 and 4. You can pick any antiderivative you want. I chose the case where c was equal to 0 here. This means that we are looking at 1/6 sine of 3 times 4 squared plus 5 minus 1/6 sine of 3 times 2 squared plus 5. And I'm just going to leave this in the format of 1/6 times sine of 48 plus 5 is 53 minus 1/6 times sine of 12 plus 5 is 17. So this is using the fundamental theorem of calculus with u-substitution involved, where we go completely to the end of the antiderivative in terms of x. Method 2, if a definite integral involves u-substitution, is to convert the bounds when we do our into u. So we'll convert the bounds into u. And then apply the fundamental theorem of calculus in u. So for an example, let's go ahead and evaluate the definite integral from 1 to 5 of, in parentheses, 3x minus 1, end parentheses, times e to the, in parentheses, 3x squared minus 2x plus 5, end parentheses, dx. So if we wish to go ahead and do this definite integral, our u-substitution, our inside function is at 3x squared minus 2x plus 5. So let's go ahead and set u equal to 3x squared minus 2x plus 5. Then we have that du is 6x minus 2 dx. All right, so we have our du is 6x minus 2 dx. So at this point, we are looking at we have e to the u times 3x minus 1 dx. But note, 3x minus 1 dx is just 1/2 times 6x minus 2 dx, which is just 1/2 du. So we know that we are looking at a definite integral, and we just have e to the u times 1/2 du, or 1/2 e to the u du. And now we need to convert our bounds. So for converting our bounds, the 1 should go to our lower bound using the fact that u equals 3x squared minus 2x plus 5. So x equals 1 would mean that u is equal to 3 times 1 squared plus 2 times 1, sorry, minus 2 times 1 plus 5, otherwise known as 3 minus 2 plus 5 is 6. So we are going, our lower bound becomes 6. Our upper bound x equals 5 means we have u is equal to 3 times 5 squared minus 2 times 5 plus 5. That is 75 minus 10 is 65 plus 5 is 70. So our upper limit is 70. So we are looking at the definite integral from 6 to 70 of e to the u times 1/2 du. Integrating 1/2 e to the u just becomes 1/2 e to the u, and we are evaluating from 6 to 70. So we are looking at 1/2 e to the 70th minus 1/2 e to the 6th. These two methods are absolutely equivalent. Essentially, we don't do the plug in u equals blah 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 stage once we've taken the antiderivative here, but the bounds are that plug-in. Right? We plugged in our x over on the left here to get our bounds. So personally, I usually find the changing of bounds the easiest one, just so I don't have to worry about forgetting one way or another. But you're welcome to use either approach for the definite integral. So either you can take the entire antiderivative, converting back to x, before you apply the fundamental theorem of calculus, or you can convert your bounds to u and apply the fundamental theorem of calculus in u. In the next video, we will go ahead and do one more example of finding a definite integral when u-substitution is involved.